Awesome, everyone. Thanks for joining in. One more Advanced Network Management class. Today we're going to be discussing the most important topic of the semester, Alvin. And that is virtual private networks and IPsec. Alright, so we're going to get started with module number 8. I have divided this lecture into a few topics. The first topic we will discuss is virtual private networks technologies. We're going to talk about the types of virtual private networks and IPsec. So get started with the first topic, VPN technology. Mate, if you were here when COVID hit, oh my goodness, right? It was so rough and people were just going home, started working from home, all these crazy things going on. But the thing is, at the time, about 2020, right? When COVID hit for the first time. So about 2020, all these companies, they started to send people home. And the biggest issue in sending people home was that if they were working in the office, they had all those shared folders, they had all their files, they had all the software installed in the company's network, in the company's computers, yeah? They had Active Directory, they could log into many computers and stuff like that. But the thing is, once you send people home, mate, do you see the security risk? Because now they rely on their own machines. And mate, when people rely on their own machines for security purposes, things go wrong, okay? Many bad things happen. For example, I teach a whole bunch of backup in many courses. I don't even remember the last time I had a backup myself for any of my files. So it's really hard when you talk about your own personal security. When it's your job to do something, much easier, right? But yeah, you got the big picture. So what I actually want to say is, because of the 2020s and all these crazy things happening, and also cloud solutions being widely deployed pretty much everywhere with Azure Labs, with AWS, the need for having virtual private networks grew exponentially, mate, in the past 2 years, and it is still growing more and more every single month. The professionals that know how to set up virtual private networks, the professionals that know how to maintain virtual private networks, they are in very high demand. When we're talking about virtual private networks in this course, don't think about just the software that you pay some money every month to get it. It's not for personal use. We're talking about virtual private networks for company use, mate, for enterprise environments. It's not the sort of thing that you go to a NordVPN, you get a $99 subscription for 2 years or something like that, Fred, and there you go, you are secure. We're not talking about that, mate. We're actually talking about enterprise level solutions for virtual private networks. Awesome. So this is an example of virtual private networks, and this is actually telling us why virtual private networks are so important nowadays. Many years ago, probably 10 to 20 years ago, we started learning networking. Doesn't matter where you were studying networking. When I was doing my master's, I was actually studying networking probably 10 years ago. And the teachers were like always talking about something called a lease line. Oh, a lease line, a company can get a lease line from an ISP, and then they can have a private connection and stuff like that. But the thing is, a lease line is super expensive, all right? And it's not widely available to the public. Medium enterprises, they will have a hard time trying to get a lease line, okay? So the ISP will only provide a lease line because the lease line has a lot of money involved. They have to lay the cables, they have to install all the infrastructure, yeah? So they will only do it if they see an actual benefit in doing a lease line for a customer. What that means is most of the time the medium enterprises, medium companies, they will be relying on the public infrastructure, the internet, the public internet infrastructure. There is a problem with the public internet infrastructure. What's the problem with it?
It's public.
It is public. You don't know what's out there, mate. Alright? So I'm going to tell you something. The internet, Andrew, is a pretty shitty, scary place, mate. Yeah? You have the dark web, deep web, all these sort of stuff, yeah? Out there on the internet. And it's all public. You don't know who actually owns a portion of the internet. I have to go back, mate. For your first semester at CIT, you're probably doing Introduction to Networks or Network Essentials. Is that right?
Yeah.
Who's your teacher?
Network Essentials.
Maybe Sam Caruso? Daniel Sam Caruso, yeah?
Alan Brew.
At that time, Alan was pretty good, man.
It's great.
At that time, you heard something from the teacher. The teacher actually asked you a question. Who owns the internet?
Yeah.
Who owns the internet? What's the answer to this question?
Many entities.
Nobody.
Yeah, the answer was
Nobody.
nobody, right?
Bunch of people.
The teacher actually told you nobody owns the internet. And I'm going to tell you that if I was the teacher, I wouldn't have said that because I hate these definitions. Because that's not actually quite true. Sorry to break your heart, but that's not actually quite true. Because when you say nobody owns it, that means you can take hold of it. Yeah? No one cares, I'll just take it for me, right? All the devices, everything out there in the internet, I can just take it because no one owns it. But that's not the truth, man. The truth is the internet is made up of everything. A little bit of every single company. So it's actually the right answer to this question is everybody owns the internet because every single person, every single company owns a portion of the internet. So if you want to buy Mr. Alvin a server from Allbeats and you want to have your own web page in your house, you can do it, man. Yeah? You just got to make sure you have a public address and then you can pay for a domain name register to register your DNS to your public IP address. You configure your router to do port forwarding to your server. There you go. You have a server which is on the internet. But you own the server, don't you agree? Yeah? The server is yours, it belongs to you. Yeah? But it's now part of the internet. So how do you explain that? Yeah? So the internet is actually a little bit from everybody. Yeah? ISPs, they have a whole bunch of networking equipment that they own. Other ISPs, they have the same. Some domain name companies, they have domain servers. They have hosts. They have a whole bunch of things, man. When you connect all these things together, you get this internet. And because of these, man, it is even more scary, isn't it? Because you're sending your traffic, you're sending your data into all these equipment that belongs to other people, and you don't know what they can be doing with it. Yeah? For example, if Alvin has his own web server for his own web page and stuff like that, if people from the internet try to access his web server, he can maybe copy all the files that they're sending to the server, or all the files that the server is sending to them, and things like that. Isn't that scary? It is, man. It is pretty scary. Right? And because of these, mates, so the companies, they have to rely on the internet infrastructure. But the thing is, how can they rely on something that nobody owns? How can they rely on something that they will have to send data and they don't know who is going to be there to see it? What's the answer for this, mate? Encryption. Yeah? So instead of just sending the data as it is, they will do some sort of encryption to make sure the data is hidden. So they will be sending the data through the internet. But now this time the data is encrypted. It's hidden. And we're representing this by the tunnels. Every time you see a tunnel such as this one here, it just basically means from end to end there is some sort of encryption. So this is like a virtual tunnel. This connection doesn't necessarily exist as it is physically. So physically speaking, there might not be a direct connection between these two here. But still, if only these two ends know the encryption algorithm that is being used, know how to hide the information, it's like they have a virtual connection between them, which is secure. There are many, many more things included in the VPN technologies as well. Not only encryption, but hashing as well. Right? So do you guys remember what is encryption? And what can encryption do for you actually?
Encryption brings the element of the CIA file.
Yes.
So
which is confidentiality.
Yeah.
Yeah, remember confidentiality? We discussed about this in the network security class.
Yeah.
What is confidentiality?
That the information is not revealed or is not visible, or is not clear to, third parties,
Unauthorized.
unauthorized
people.
people.
Yeah, exactly.
People.
That's exactly what it is. That's confidentiality, encryption. Now check it out, mate. I like to think as the internet as just like public places. Yeah. Think about the mall, Mr. Alvin. Do you go to the supermarket naked? Do you? I wouldn't do that. If you'd like to do that, it's up to you, man. But the thing is, if you do it, you're just basically showing everything you've got, Mr. Alvin, which may not be a good thing, right? Not for you, not for other people, yeah? So when you don't have encryption and you're using the public infrastructure, mate, it is like going to the supermarket naked. You don't know who's going to be watching you. You don't know who's going to be taking pictures of you. This analogy is so good. Yeah? So you don't want to be going to the supermarket naked. So if the companies, they have many branches, many offices, and they rely on the public internet infrastructure, they don't want to be sending the data as it is. The raw data. The naked data. Yeah? They don't want to be sending as it is. They want to establish these virtual private network connections, which we call the VPN tunnels. And this is exactly what we're interested in here, right? All right, the benefits of having a VPN, of course, it will save money. And that's because the alternative would be having a lease line. A lease line is expensive. Security. You will have the CIA tried in place every time you set up a VPN. So you will make sure you have confidentiality, integrity, and availability. So we spoke about confidentiality already and how you can guarantee confidentiality, which is through the use of encryption. Now, how do you guarantee integrity? Because even though you're sending your data here, someone can still be here modifying the data, even though they cannot see it. They could be modifying it, tampering it, changing it. All right? So how can you guarantee it's going to be integral? Remember we discussed integrity? Making sure it's unmodified, unaltered, unchanged. And that is as far as my English dictionary goes. All right? So there you go, it's unchanged, unmodified. And you guarantee that with, Fred?
Hashing.
Hashing. All right? Hashing is a one-way algorithm. Here's the big difference between hashing and encryption. Encryption is a two-way process. You want to hide it, and you can unhide it if you want. You can show or hide. Yeah. So you send it as encrypted. At the other end, you decrypt it, and you get the information back. That's what encryption is. In hashing, it's not important to get the original data back. Right? But it's important for you to double check if something is unaltered. Did I tell you guys the analogy about hashing so you can understand hashing better? Did I tell you that? No? Hashing, mate, is like blending a juice. Right? So I'll give you a recipe, Andrew, for a green juice. Right? You follow the recipe, you blend all the ingredients in the right proportions, yeah? You drink the juice, all right? Tomorrow you're gonna go somewhere else. You still have the recipe and you still have the ingredients. You will follow the recipe again, you will blend all the ingredients again, and given that you have the right proportions again, the juice should taste the same. Yeah? If you blended the juice yesterday without salt, today you blend it again, but you put salt, it's gonna taste completely different, isn't it? But why am I telling you this blender analogy? Because the hashing is the same, it's one way. You won't be able to unblend the stuff and magically make the ingredients happen again, exist again. It's not gonna happen. So there you go, analogy for you. All right, scalability. VPNs allow organizations to use the internet. Mate, the internet is huge. All these public connections, public infrastructure, all the ISPs. Now you have scalability all around the globe. There's a fiber optic cable, for God's sakes, from Australia to the US. Yeah? So you're connected everywhere and anywhere. Compatibility. VPNs can be implemented across a wide variety of WAN link options, including broadband technologies. In other words, it doesn't matter the transport medium. It doesn't matter if it's Wi-Fi, it doesn't matter if it's 4G, it doesn't matter if it's 5G, it doesn't matter if it's fiber optics, it doesn't matter the medium, right? You can still create a VPN for virtual private network traffic. There you go. A site-to-site VPN. So the one you have, Mr. Shai, that you probably pay some money to a company, yeah? NordVPN or whatever that is. Fast VPN, NordVPN, Tunnel Bear. What else is up there?
Cisco AnyConnect.
So many, Cisco AnyConnect. So many of them, alright? So you pay this some money, but what you actually have is something called a client VPN. Why? Because you need some software installed for your machine to be able to encrypt, decrypt the data, yeah? And to send the traffic and receive the traffic. So that is a client VPN. When we talk about site-to-site VPNs, we are just creating the VPN tunnels and guaranteeing encryption up to the edge router. Because, after all, the private network should be fairly secure. Yeah? Private network should be fairly secure. Given that you have all the firewalls, the access control, this and everything here, should be fairly secure compared to the internet, right? You have to agree with it. So there you go. So this is what is usually done. And this is better than the client solution, because in the client solution, every client has to connect to the VPN. Every client needs to install the necessary software. Every client needs to disconnect from the VPN if they need.
Authenticate.
They have to authenticate. They have to put their username and passwords and all those sort of things. That is not scalable if you think about a company with 500 employees. How are you going to educate all these 500 employees to log in every single day, to authenticate to their accounts, to make sure they click in the connect button, to make sure they double check if they're actually connected through the VPN and not the normal network? Yeah? How are you going to do that, mate? It's not feasible. So what most of the companies do nowadays is this. Site-to-site VPNs. So site-to-site VPNs in the industry nowadays, they are done through something called DMVPN, alright? Or GRE over IPsec, which is another type of technology that we will discuss here. DMVPN is a little bit more scalable because you will have multiple routers usually. You have a company that owns many branches, many offices, all over Australia, for example. How are you going to make sure the traffic going from one branch to the other branch is secure? Through the DMVPNs. Now, GRE over IPsec can also be used, but GRE over IPsec is usually done when you just have two endpoints. For example, two routers. Right? But don't worry too much about it. We're pretty much going to stay just with GRE over IPsec as a VPN solution. Okay. Alright, so for this course, you only learn how to set up a VPN tunnel between two routers maximum. Okay? Because if you have many routers, it's way more complicated. So that's as far as we go. Now, in terms of management, VPNs can be managed and deployed as enterprise VPNs and service provider VPNs. Of course, the enterprise VPNs, they're a common solution for securing enterprise traffic across the internet. Site-to-site and remote access VPNs are created and managed by the enterprise using IPsec and SSL VPNs. So SSL is also another way that we can create the VPN tunnels. Alright, service provider VPNs, they are created and managed by the provider network. The provider uses MPLS. So in the service provider VPN, which we will not cover in this course, is more if you're going to work for a telco company. Then you're going to be setting up VPNs using MPLS, which is multi-protocol label switching, to actually switch the packets instead of the IP address. Okay. That's a little bit way too advanced for us. We don't study this.
So the service provider VPN is more of like an internal VPN for a company, even though it's provided like Telstra might be the.
Yes, so when you say for
they're
company,
like a service provider for a government department that has 3 different places in Canberra, then the connections between them will be done using that, or.
yes, it can be done using the service provider VPN. So for example, if you have a government agency and they have a single contract with one ISP,
Yeah.
let's say Optus. So many Australian government departments, they have a contract with Optus,
Yeah.
but they have many offices. So instead of actually developing the enterprise VPN by themselves,
Yeah.
they will discuss the alternative with the service provider. They will pay them some money and they will basically transfer the job to the ISP. And the ISP will create the tunnels and they will create the VPNs based on MPLS. But yeah, that's as far as we go here. There's a lot more on top of that. Yeah. All right. Types of VPNs. So remote access let remote mobile users securely connect to the enterprise. So it's very nice that we can create these site-to-site VPNs, but sometimes we have the users, the employees, that would like to work from home. And whenever they like to go home and work from home, they don't actually have the expertise to create the tunnel from their home router to the enterprise router. So site-to-site VPN is not a solution if you have remote employees. It's not a good one. So a solution would be a remote access VPN. So you could install the necessary software in the person's computer, personal machine, and then you give them instructions. Would you like to connect to the private network of the company? You have to do this and that. And then every time they go home, they try to work remotely, they have to follow the procedure. Right? So most of the companies that they have a bring your own device policy, that will actually allow the employees to bring their own computers, they will usually tell them that they need to install something like Cisco AnyConnect to be able to access the internal private network resources, the files, the folders and everything from the private network of the company. All right, and then we have clientless VPN connections. The connection is secure using a web browser and client-based VPN connections. So with the clientless VPN connection, you don't necessarily need specialized software. Why? Because you're going to be relying on an SSL connection. And SSL is widely deployed on browsers. Yeah, the padlock. Yeah, HTTPS, you get a certificate, blah, blah, blah. Yeah, there you go. That is called a clientless VPN because you are not required to have specialized software. Just your browser is enough.
Just a question about this one. So when you create a site-to-site VPN, you can create it based on IPsec or over SSL as well between site-to-site? Site-to-site can use IPsec or SSL?
Yes.
So you can?
Yes.
And when you're using a client VPN from user's machine at home to connect to the VPN as well, you can also utilize
Both.
SSL and IPsec?
Both. But the difference is it will be either clientless or client-based.
Clientless.
If it's clientless, you just need the browser.
The client is
Because
only
after
for
all,
SSL, right?
It's running on top of SSL certificates and stuff.
Yeah.
But then if you're actually running something more specialized with IPsec or something more,
Yeah.
customized, you will then need the client-based VPN connection. You actually need the proprietary software,
Yes.
for example, Cisco AnyConnect or something like that, to be able to connect.
But even
To
if
the
I'm
VPN.
using a client-based connection, I can utilize the SSL framework or option?
Yes,
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 not
Yes.
just the IPsec one.
yes, still.
Just if it's clientless, it definitely will be SSL because it's based on web browser.
Yes, exactly.
Yeah, all right. Thank
Exactly.
you.
So this is just like categorizing two different types.
Options.
If you need the necessary software or if you can just use your browser, that's it. All right. In this example here, what we actually have is the SSL VPN tunnel. So most of the companies, they will have some appliance, yeah, could be an advanced security appliance with SSL VPN capabilities. It would just basically allow customers to connect to an SSL VPN tunnel using the web browser. This is if you use the web browser alternative, you're using the clientless VPN. Or if you're using proprietary software, Cisco AnyConnect is one example, you will be running the client-based because you need the software. And it's a specialized software just for that.
So when you say client, it's just basically a piece of software that's on your computer, right?
Yes, yes. For this terminology, yes. So clientless, you don't need the necessary proprietary software to connect to the VPN. Client-based, you need the client software. So client here is actually referring to software.
Yeah, little app.
Yeah.
So the client that relies on the operating system. So
Browser.
is HTTP on the browser only?
Yeah, HTTPS, and then you get the certificates, SSL certificates.
So when now log into ELAN, for example, that's a clientless VPN.
Yes, it is. Yeah, yes,
so
it is.
your banks and
It's
everything.
HTTPS.
Yeah, exactly.
Yes, it's
Yeah.
using an SSL certificate.
Yeah.
Yes, it is.
Yeah.
It is a type of VPN.
What, when you log into ELAN?
Yes, if it's using HTTPS and it's using an SSL certificate, it is considered to be a clientless based VPN. But it's a VPN just for the connection and just for transferring HTTPS files. All the other files are unsecure. That's the thing. All right. Now, few differences between IPsec and SSL. So we've got application supported. IPsec is extensive. All IP-based applications. SSL is limited. Only web-based applications and file sharing is allowed for SSL. So that's your famous HTTPS. You have an SSL certificate. You have some sort of encryption between your device, your browser, and the server, the destination server. And then you've got authentication strength. Of course, you have much more strength in IPsec because you have a much more wide range of encryption algorithms available. SSL is moderate. Okay? Moderate encryption, not the highest standards, but it's enough. For the encryption strength, we got strong, key length from 56 all the way to 256 bits. And for SSL, depending on which key you use, it would be considered to be moderate or strong. For connection complexity, for IPsec, it's medium, requires VPN client installed on a host. If you are running the client-based, if you're running site-to-site, you don't need it. You just need the two routers to communicate using IPsec. And all the clients don't even need to know that there is a VPN tunnel between the routers. As a matter of fact, they won't even know. Okay. And then we've got the last option up there, which is connection option. So connection options, we have very limited amount of options for IPsec, and we have extensive connection options for SSL because after all, SSL will run on top of a browser event. So it could be running pretty much on any machine, even on your phone. You could have an SSL web page that is encrypting using SSL, encrypting the traffic using SSL. All right, site-to-site VPN, like I said, the client has not even a single idea that the traffic is being encrypted. All the encryption is done at the gateway or at the edge router. The edge router will be doing encryption and decryption. The client machine doesn't even need to know. All right. Now, all these VPN technologies that we deploy site to site, they will rely on the tunnels. The tunnels will basically means there is a virtual connection between two routers, even though this connection is not physical, even though it's going through the internet infrastructure, it looks like it's an end-to-end connection. So that is done through GRE tunnels. You create a virtual tunnel. So you only have two ends of the tunnel, even though you have multiple connections through the internet. Now, a GRE tunnel can encapsulate various network layer protocols as well as multicast and broadcast traffic, which is amazing because you basically have a GRE tunnel. You can, for example, have all your clients in your private network running a different protocol, a completely different protocol. All right? And you can still have the GRE tunnels encapsulating the traffic in a different protocol. That is crazy. So for example, you can have a GRE IPv4 tunnel, so you have both ends IPv4, but on the internal side of the network, you can be running a different protocol, for example. But the tunnel where the traffic will be going through can be running a different protocol. A GRE packet, a GRE tunnel by itself does not have encryption by default. So you can form these GRE tunnels, these virtual tunnels, but they don't have encryption by default. You have to configure encryption on the go, and you will rely on IPsec. If you don't remember, IPsec is a framework for encryption, hashing, and many other things. Protection against replay attacks and a whole bunch of other things. So there you go. This is how a GRE tunnel looks like. So what you basically have is you have your standard IP packet here. What you're basically going to do is you're going to insert an additional packet header with a different IP information. So for example, this could be an entirely different source and destination IP address, and this could be an entirely different source and destination IP address. So it's like it's encapsulated twice at the network layer level. So that basically means the first device that receives it will read this, and then it will forward it like this. And then the second device will read this, and then interpret the data. And this is how you form the tunnels. Because it will basically look like it's a direct connection, even though it's not. The internal components are actually with a different source and destination IP.
So the yellow part is being encrypted. The yellow part is being encrypted, or just the data part?
So
payload?
that's the thing. So this is just GRE. Just GRE by itself doesn't have any level of encryption.
Okay.
So you need to add it with IPsec. When you're doing IPsec on the packet like this, you have two different transport models. Tunnel mode and transport mode. In tunnel mode, you basically take the entire content of the packet. You're going to encrypt it, and you're going to put another layer of destination and source IP. For the transport mode, you're going to keep the headers as they are, and you are only going to encrypt the data. So there are two ways you can do this. Transport mode and tunnel mode. Okay. I like to think it like every time you take a tunnel, everything goes through the tunnel. And if it's just the transport, it's just the data. That's an easy way to remember.
When you're doing tunneling, don't you have to create the two session keys within the...
Yes, you have to do that for the second assessment. So you have, in the second assessment, what you basically have is you have 3 routers in a similar topology that you had to do for the first assessment. But this time, you basically have to create a site-to-site VPN between only 2 routers. Even though the traffic will go through all 3, it will look like the traffic is going directly from one to the other. And of course, you have to encrypt it, you have to configure hashing, you have to configure everything. All the session keys, absolutely everything.
And that's on Azure, is it?
Huh?
And that'll be in Azure.
Yes, yes. All right, so there you go, we have an example here. This, by the way, where it says GRE tunnel, original IP packet, IPsec VPN, this is not a physical connection. This connection here doesn't exist. These 2 routers, they are connected to the internet. But you can make it look like they're directly connected. How? Through a GRE tunnel. So if you establish a tunnel between these 2 devices, this will have an IP address, this will have an IP address. So for example, you could set up a network here, 10.1.1.1, 10.1.1.2, and it will look like they're directly connected. But the thing is, the traffic is being encrypted. So you have 2 encapsulations happening at the network layer. You have the standard one, and on top of the standard one, you have the tunnel encapsulation. So that's how you have so many, you have another address on top of addresses that already exist. So for example, you could still have private addresses here in the tunnel, but they actually have public addresses to the internet. Isn't that right? But it will still look like it's an entire private network, because all the addresses you're using are private. And these private addresses, they only exist for these two guys, they don't exist for the internet. That's what the GRE tunnel will allow you to do.
So GRE tunnel is a bit like making a special type of encapsulation. I know I might be saying the same words, but it's making a special type of encapsulation on top of the encapsulation
That already exists.
And then the outer layer, which is the GRE encapsulation, it does all the work for movement through the internet.
Yeah.
The inside transport layer.
So let's go.
one doesn't get-
Let's review certain things here. What happens? So if you have this network here and you want to communicate with this email server, they are both in the private network, right? One is at the branch office, the other one is at the headquarters. How does the traffic flow normally without the VPN tunnel? Your traffic will go to the switch will send to the default gateway because destination IP is not in the same network, so it sends to the gateway. The gateway will receive the packet, it's coming from a private IP, it has to send to the public infrastructure which has a public IP. So it will do the network address translation. It will translate the address, send it here through a public IP address. The destination will be your headquarter routers with the public address. Yeah. And it will then be sent out to the web server. Yeah. So let's say this email server this headquarter routers is of course doing the PAT, port address translation. So it will just basically be forwarding to the email server. So this is without encryption, without tunnels, without anything like that. Right? But the thing is, you don't necessarily need the public IP addresses on your infrastructure. They can still exist physically, because that's the way the router will go out. But you can configure these two routers, for example. So this will be in the same local area network for the GRE tunnel. So you have 10.1.1.1 here, 10.1.1.2 here. And then you can configure these two routers to communicate through a routing protocol. So these router will tell about this network to these router. Yeah? Sort of thing. But then, once this router receives a packet, it will check the routing table. The routing table will say, you have to go to 10.1.1.2 to reach the email server. And then this guy will say, oh, 10.1.1.2. 10.1.1.2 is the GRE tunnel or the end. But the GRE tunnel or the end is only mapped to the public IP address of the other router. So this guy will actually send it to the public IP address of the other router. But in the routing table, it looks like it's going directly. So it's just another mapping on top of what it already exists. So it looks like it's going directly. Yeah, man. It is quite complex, but it is really nice and smart. So the final result is that if you have a very nice encryption technology here, very nice hashing here and everything else, it looks like this is an internal single private network, even though they are not even in the same location. That's why you've been learning all these different topologies. So the topology that you did for assessment number 1, you had 3 routers. And then you have local area networks. And you'll be like, do you know when you see that, exactly that in the industry? Never. Right? What you will see is, it will look like that, it will look like there is a direct connection between the routers, but there isn't. It's actually going through the internet. What is there would be a GRE tunnel.
If you intercept the packets on the way, and let's say you eavesdrop or you're using a tool to look like a wire shop to see the traffic, right? You'll see the public IP addresses, the external one on the GRC encapsulation.
The source and destination, yes.
You will see the external
Yes.
if it's not the tunnel mode. If
Yes,
it's transit mode, you can see the IP addresses, right?
yes.
If it's transit mode, by the way, everything is encrypted. So how can it route to the internet if the routers on the way can't see the?
That's the thing. So in tunnel mode, you will encrypt the whole thing here,
Except the IP.
except this, because you still need that for routing.
Yes.
And in transport mode, you leave this open and you just encrypt this.
Yes.
Doesn't matter if the person sees this. It's just the end of the tunnels, but they still don't know what the data actually means. So it is actually recommended, because this pretty much doesn't matter if people see this. It is actually recommended as a best practice to set it up as transport mode, because there is less overhead,
Yeah.
because you're encrypting less stuff. So it says there's less overhead. So on all these senior network engineering textbooks and stuff, people that have been doing this for a very long time, the best deployable method is transport mode. Yeah, that's actually the one that Cisco recommends at the CCNP and CCIE level. Yeah, and I just know because I was studying that.
Down the bottom of that slide, it says, you're probably going to talk about it, are you going to do IPsec in a minute?
Yeah, IPsec is just a framework for protecting the GRE tunnel. Because the GRE tunnel doesn't have encryption, doesn't have protection by itself. So if you just set it up a GRE tunnel, it will look like the traffic is going directly,
Yeah.
but there's no protection whatsoever. There's no encryption, there's no hashing, there's nothing. It's just a framework for you to build end-to-end connections on top of a physical infrastructure. Okay? So that's it.
So where,
There are actually two terminologies you have to learn here. There is two things. One thing is called an underlay network, and the other thing is called overlay network. What is an underlay network? Is the actual physical medium, the physical connections. So that would be all the connections to the internet. But the overlay network, the one that is on top, sits on top and it's like a virtual network, is your tunnel. Because if you look at the network itself, you will just see this. So if you configure the GRE tunnel and you do a trace route, do you know what's going to happen? How many hops will you see in the trace route? If you do a trace route from here to here, how many hops away are you? 3?
well, it should be one, because there's one routed to another router.
Who thinks it's 1?
I'm gonna
Who thinks it's 1? 2? Who thinks it's 3? So everybody else thinks nothing. Alright. It is actually 2. So no one got it right. For God's sakes, you guys don't remember how to count the hops? Man, every time you think about a hop, mate, think about a kangaroo. You're in Australia, mate. So think about the kangaroo. The kangaroo likes to jump the routers. Alright? So the kangaroo, the switches are too low for the kangaroo to jump. So the kangaroo will not jump the switches. The kangaroo will just jump from one router interface to another. So you imagine your kangaroo going here. This is too low for me, I'm not going to jump.
What if the kangaroo starts?
And then he will jump this one. And when he jumps the router, your kangaroo mate, that is a hop. And then your kangaroo keeps going here and jumps another router. How many hops you have? 2. That is if you have your overlay network configured. Now, if you don't have the overlay network and you do a trace route, how many hops you have?
You don't know many.
Whatever you have on the internet plus 2. Yeah. So your kangaroo will come here. Hop. Yeah. So if you actually do that, mate, you see like a whole bunch of them. Yeah.
Yeah. Sorry for dumb questions, but I've never understood this properly before. So the IPsec then is encrypting everything except the GRE.
So,
two addresses for the GRA, right?
so there are two types of IPsec. One is tunnel mode. So in tunnel mode, it will encrypt all of this here in white.
Yep.
It's a tunnel, so we encrypt absolutely everything except the primary headers.
Yep.
Including the GLE header or not?
No.
No,
In tunnel
No.
Just
mode.
do the yellow bit.
no,
Right.
just the white part here.
That's tunnel mode.
And in transport mode, it will keep this here and it will just encrypt the data.
Alright, yeah.
And like I said, the recommended one, the official recommendation
Transport mode.
is transport mode.
Thanks.
Because there is less overhead,
I've never.
because you're encrypting less stuff.
Thank you.
Alright? Cool. There you go. Now, this can be fairly easy, mate, when you have 2 points. One router here, one router there. But the thing is, it can get extremely complex the more routers you add. So for example, think about Microsoft. You have a Microsoft branch office in Sydney, and you have a Microsoft headquarters here in Canberra. Let's say that. Yeah? Both of them are connected to the internet infrastructure. You want everything to be secure, you configure a site-to-site VPN. All the traffic going from the headquarters to the branch will be secure, even though it's using the public network infrastructure. Cool? But then Microsoft decides that they want to buy another branch office in Brisbane. What are you going to do now, mate? You have to make sure the traffic will go on all the branches and all the headquarters. Yeah? So what's going to happen?
Do you have to have two different tunnels?
So you can have something called a hub and spoke. Remember hub and spoke? You have a central device, and then all the other devices are connected to the central device, which is called the hub. Yeah? But there is a disadvantage in that. All the traffic will have to flow through the hub. So if it's a crazy amount of traffic, you have to spend a whole bunch of money for that router, because that router has to be very powerful. Does that make sense? The alternative will be DMVPNs. DMVPNs actually allows us to create these tunnels automatically. So you just need to set up what's going to be the hub, and all the other ones, the spokes, they can form tunnels to the hub automatically. So they don't have to send traffic only to the hub. And they can also form tunnels between themselves as well without going to the hub. That is done through this technology here called DMVPN. Now DMVPN is one of the technologies that is here to stay. I'm gonna tell you, I have seen so many job ads lately saying that the network engineer should be able to know how to configure DMVPNs. But that's more for like senior positions, not for entry level. For entry level ones, you just fine knowing GRE and GRE over IPsec. But for more advanced positions, DMVPN is the thing, man, that you should learn next.
Is there a similar protocol for other providers? Because you say...
DMVPN is not a protocol.
No, but I mean, is DMVPN is only a Cisco thing, or are there other things when you're not a Cisco?
Yeah, there are other solutions as well out there in the industry. Yeah. All right, cool. So this is how it's going to look like. You have your virtual tunnel interface. Now, if you're using IPsec, of course, you will be protecting your GRE tunnel. You will have encryption and hashing and everything else in your connection. And then you'll be forming an IPsec virtual tunnel interface. All traffic going from the branch to the headquarters will be encrypted, will be secure. Alright, MPLS can provide clients with managed VPN solutions. There are two types of MPLS VPNs, layer 3 MPLS VPNs and layer 2 MPLS VPNs. As the name suggests, a layer 3 MPLS VPN, the service provider participates in customer routing by establishing a peering between the customer router and the provider's router. So if you have a layer 3 MPLS VPN, it looks like the ISP is a router. They will give you an IP address on one end, and they will give another IP address in the other end. and it looks like the ISP is a big router doing all the routing for you. When you have a layer 2 MPLS VPN, it looks like the entire service provider is actually a switch, because you will be getting this an IP address which is in the same network for both of your devices. So it looks like the ISP is just a switch, forwarding the traffic. So these are two ways that the ISP will do MPLS VPNs, layer 3 and layer 2. IPsec. So the purpose of IPsec, the IPsec protocols I explained in the video, so make sure you watch the video later. There is an IETF standard that defines how a VPN can be secured across IP networks. IPsec protects and authenticates the packets between source and destination, and of course it involves the CIA triad that we already discussed. So confidentiality is guaranteed through the use of encryption, integrity is guaranteed through the use of hashing, origin authentication uses the Internet Key Exchange, IKE, to authenticate source and destination. Do you guys remember what IKE is used for?
Do that in Safari. We didn't do that around in switching.
What is IKE?
Is it used for
IKE.
SSL?
Internet Key Exchange. The name is pretty self-explanatory if you think about it.
Is it like the public-private thing?
No. So check it out. For encryption, you need to have a key to encrypt, and you need to have a key to decrypt. If you have symmetric encryption, what does that mean? It's the same key to encrypt, the same key to decrypt. If you have asymmetric encryption, it's a different key, but you still need a compatible key to decrypt it. But the thing is, if two routers are talking to each other, and this guy will say, okay, let's encrypt the traffic. I'm sending you encrypted traffic. And this guy was like, okay, I got the encrypted traffic, but how do I decrypt it? I don't have the key. So IKE is actually a negotiation protocol for these two routers before they start sending encrypted packages, for them to negotiate the keys. Hey mate, I'm gonna be encrypting traffic. And then the guy says, okay, cool. What are you gonna do to encrypt the traffic? And then this guy will say, I'm gonna use this key. But the problem is, if it sends the key to the other guy, someone can take it. And then you have an issue. So usually IKE will use something called Diffie-Hellman algorithm. Remember the Diffie-Hellman? So instead of actually handing out the key, there is a protocol, there is some algorithm, some mathematical algorithm that we will allow this guy to give some hints to the other guy, and then the other guy can generate the key without actually receiving the key. So it's very, very complex. What you just need to know is that they're not actually exchanging the key. They're actually negotiating the key in a way that they don't actually necessarily need to transmit the key itself. Yeah. There you go. Your Diffie-Hellman.
Why can't someone just negotiate the same key?
Why can't someone negotiate?
You know, if this router gives this router sort of, say, some hints, why is it that someone else can't hear those hints and just know what they're talking about?
Yeah, it's quite more complex than that. It's just not only knowing, but they also rely on something that only each other know.
Yeah, right. Is that because they're Cisco routers? Or?
Yes.
Yeah, yeah,
So
right.
is it like a maths equation and they have the answer and it has to match?
Yes, exactly. So they're not actually sending absolutely everything. They just
But
Yeah.
I was wondering, if someone else had a Cisco router though, like secretly plugged in,
no. It's a bit more complex than that.
is it?
Yeah.
Okay.
There's a question.
Because you also need.
The second key would be
Yeah.
So in order for like encryption to happen, the first key must match the second, therefore it decrypts the.
And you will,
from an like a linear address.
and the thing is, you will also configure a pre-shared key on both.
Oh, you.
So both will have a pre-shared key.
Oh, okay, yeah.
So for example, you say your pre-shared key is Cisco, your pre-shared key is Cisco.
Yeah, right.
So only both of them have the pre-shared key
So
to send these hints to each other about the
So you physically
encryption algorithm. Yes, you still
Exactly.
Exactly. Exactly. Yes. To basically authenticate them before they start sending the hints for encryption.
So they're not. So someone listening.
Exactly. So if someone else is listening, they don't have the pre-shared key to understand the hints and to understand the messages, to then find out what encryption is being used. Yeah. So there you go. Awesome. So this is how it works, all the protocols. So at the IPsec protocol, we have the authentication header, the ESP plus authentication header. What you basically have to remember from here is that at the authentication header, we don't have encryption. We just have hashing. So we have integrity and we have, what's the other one? So we have integrity and authentication. So you have authentication and integrity, but you don't have encryption at the authentication header. At the ESP header, it's where everything will be encrypted. So at the authentication header, you will be doing the key exchange, the IKE, and then the ESP will be your encrypted packets and stuff like that. It will contain everything else which is actually encrypted. Alright, so in terms of confidentiality, we have the different algorithms. For integrity, we have different algorithms as well, authentication and Diffie-Hellman. So confidentiality, we have here in order of the least secure to the most secure. Right? So DES is pretty much dead. Triple DES, pretty much no one else is using it in the industry anymore. They were proving to have some vulnerabilities in terms of encryption. AES is still quietly used in the industry. SEAL is starting to be implemented in the industry. So most likely you will see AES in the industry. Integrity, we have MD5 and SHA. MD5 not considered that secure anymore. SHA 1 is quite not secure anymore. Recommended SHA 256 and above. Right. And then we have pre-shared key and RSA for means of authentication. And it's just basically setting up the pre-shared key for PS key. And the RSA is through the use of certificates. So instead of putting the shared key on both, because if someone finds out the shared key, they can get in, you will have to install the certificate on the device and then install the same certificate on the other device. And then you have the Diffie-Hellman algorithm levels, so you can negotiate the encryption algorithm being used without exchanging the keys themselves. There are many levels of the Diffie-Hellman algorithm. Recommended is the higher the better. Because the higher the Diffie-Hellman algorithm, it basically becomes more complex. So the hints are more complex. It's harder to guess, and then.
So the router actually applies that Diffie-Hellman to the shared key and then typically gets something that creates the
No, you have the pre-shared key just for them to be able to authenticate each other, right?
But Diffie-Hellman
And then
authenticates each other, do they?
no, Diffie-Hellman is just for them to negotiate the keys that they will use for encryption. And Diffie-Hellman will not send the encryption algorithm, hey, use this encryption algorithm. No, it will not do that.
That's already been very confusing.
Yes, so you actually do the mathematical calculations and everything else to find out which encryption algorithm will be used.
Okay, so that's a negotiator.
Yeah. All right, there you go. We have an example here. This is actually confidentiality. Yeah, so you basically want to send a packet that contains information, personal information. Of course, Jeremy needs to be paid the $100, and Gail will basically transfer money to him. Of course, this has to be encrypted, right? Because if this is a request to a bank's web server or something like that, this could be changed on the internet by someone else, for a man in the middle, for example. And then, yeah, basically transfer the money to his account instead, which is an issue. So that's why it's so important to have some sort of encryption here, because then even if there's a threat actor on the internet, they will basically see a whole bunch of stuff that doesn't make sense. So even though he will change stuff here, he would not even know what that means to be able to change anything. If he changes something here, you still have integrity going on with the hashing algorithm. So still the other guy will say, okay, this is not integral, just get rid of it. So there you go. All right, yeah, in terms of confidentiality, as mentioned, we have the highest secure one, the most secure one here on the right, and the least secure one on the left. For integrity, pretty much the same thing as well. SHA to the right, MD5 to the left, the most secure one being SHA. This is the original SHA, SHA-1, 160 bits. Of course, there are many other variations of SHA which are way more secure. 256, 384, and 512. And you have the authentication ways. The pre-shared key, it is very easy to configure, does not scale well because you have to configure the pre-shared key on every single one of them. And it must be configured on every single peer. With the Rivas, Shamir, and Edelman RSA, the authentication uses digital certificates instead. So instead of actually typing things, you can just install the certificate and that's it. Call it a day. In terms of Diffie-Hellman, we have the most secure one to the right, the least secure one to the left. These are all the groups of Diffie-Hellman available. All right, cool. There's another video for you guys to watch. And module practice and quiz. A reminder that you should be doing the module exams. What time is it? That's so early, man. You should be doing the module exams. If you guys are not doing the module exams, I would be concerned if I were you. Make sure you do them. Make sure you take advantage of next week's holiday and 2 weeks break after that to, catch up with everything you have to do, mate. Because just a reminder that you will have at some point to do all of them anyways. Alright? So stop procrastinating and just do them all, smash them all and get it done.
Have you been checking our progress?
Of course I am, and I know most of you guys are not doing it. That's why I'm concerned. So I checked out some people's grade books and it said 100%. And I was like, 100%? But then I checked, the person just did the first one. This is easy. Do the other ones and keep the 100%. That would be a challenge.
Robert?
Yes, Louis.
Robert?
Yeah?
Is it the exact one you're talking about?
I'm talking about the chapter module exams in Netiquette.
The group exam.
You have to.
Oh, yeah, okay, yeah. I'll start my soon. I'll do that.
Because you guys have to do the module group exams, you have to score at least 90%. For you, it's 90, mate. No, just kidding, mate. 70.
That's okay. 90 means I know it, right?
70 for everyone, right? 70 should be enough. So 70 for everybody on all the group module exams. And on the final exam, Fred needs to score 95%. Yeah.
95?
What about Kylie?
Yeah. No, just kidding. 70 lose. 70 for everybody.
Alright, cool. Robert?
Yep.
I was going to reach out. Newbert said I was coming in 29. So I just realized that the school being in break ends. So on the 13th, I'll be coming for the Declan's assessment, which is on Thursday. So I would like to come and do the first assessment the same day. Is that alright?